applications in physics to date. When we trap antiparticles through electromagnetic fields, we can study their properties. The quantum state of particles and antiparticles can be interchanged by applying the charge conjugation, parity, and time reversal operators. To clarify, if a physicist whose body was made of antimatter would do experiments in a laboratory also made of antimatter, using chemicals and substances of antiparticles, he would find almost exactly the same results as his matter counterpart. But when they would merge, immense energy would be released proportional to their mass. Very recently, Fermilab discovered how quanta such as mesons are switching 3 trillion times per second from matter to antimatter. When we study the universe from a quantized frame of reference C, we have to take into account all experimental evidence that applies to quanta. This includes how matter and antimatter are created simultaneously in particle accelerators, and how mesons switch back and forth between one and the other. This has significant consequences when applied to C. From a quantum perspective, every instance of C has an anti-C. This explains the missing symmetry or antimatter in the universe and is closely related to the arbitrary choice of emitter and absorber in the Wheeler-Feynman time-symmetric theory. The unperturbed time t in the uncertainty principle is the required time or cycle for quanta to exist. Similar as observed in mesons, our personal experience of time or interval of the current moment reaches its threshold when C is cancelled out by its anti-C. C's interpretation of this single self-annihilating moment is framed within an abstract arrow of time. If we then want to define interaction and look at the basic properties of the wave-particle duality of quanta, all interactions would consist of interference and resonance. But since this isn't enough to explain the fundamental forces, we are required to use different models. This includes the standard model, which mediates the dynamics of the known subatomic particle through force carriers, and Einstein's general relativity, which describes macroscopic phenomena such as the orbits of planets, which follow a curvature or ellipse in space and a helix in space-time. But Einstein's model of space-time doesn't hold up on quantum levels, and the standard model needs additional force carriers to explain the origin of mass. Without success, a unification of both models or theory of everything has been subject of much research. Quantum mechanics is merely mathematical descriptions, and their practical implications are often counterintuitive. Classical concepts such as length, time, mass, and energy can also be approached with similar descriptions. By building on de Broglie's equations, we can substitute these concepts with abstract vectors. This is a probability-oriented approach towards the basic and already existing concepts in physics that allows us to unify quantum mechanics with Einstein's relativity. De Broglie's equations show how all reference frames are quantized, including all matter and all energy. Particle accelerators have demonstrated that matter and antimatter are always created simultaneously. The paradox of how reality can emerge from abstract building blocks that annihilate each other can be explained by using these quanta as the frame of reference. In a simplified analogy, we need to look at things through the eyes of a photon. The reference frame is always a quantum and defines how spacetime is quantized. When it increases or decreases, spacetime increases or decreases as well. This is reflected in quantum mechanics as the mathematical description of the probability amplitude of the wave function, or in Einstein's relativity as time dilation and length contraction. For a quantized frame of reference, mass and energy can only be defined as abstract probabilities, or if we